Somewhere out there right now, a star is burning so fiercely that its surface could vaporize steel in an instant. Meanwhile, in the darkness between galaxies, pockets of space hover just 1 degree above the coldest temperature possible in the universe, so cold that atoms nearly stop moving altogether. These aren't science fiction scenarios. These are the real, extreme temperatures that exist right now in our cosmos, defying everything we know about hot and cold here on Earth. Today, we're taking you on a journey through 50 of the most mind-bending temperature extremes in the universe. You'll discover stars so hot they're literally boiling themselves into space, shockwaves from dying stars that hit 1 billion degrees, and even places where the concept of temperature itself starts to break down. By the time we're done, you'll never look at a thermometer the same way again. So buckle up, we're about to explore the universe's most scorching and frigid corners, where the rules of heat and cold get rewritten in ways that will leave you stunned. Now let's turn our attention to the heart of our own solar system, where temperatures reach unimaginable extremes. The Sun's core is a raging furnace, clocking in at a staggering 15 million degrees Celsius. That's not just hot, it's a level of heat that makes Earth's most intense volcanic eruptions feel like a gentle breeze. This incredible temperature comes from nuclear fusion, the process that powers the Sun. Every second, hydrogen atoms collide under immense pressure, fusing into helium and releasing mind-boggling amounts of energy. To put that into perspective, the hottest lava on Earth barely reaches 1,200 degrees Celsius, meaning the Sun's core is over 12,000 times hotter. Even humanity's most extreme experiments, like the Large Hadron Collider, can't come close to replicating these conditions. What's truly wild is that this heat doesn't stay trapped inside the Sun. It gradually radiates outward, taking tens of thousands of years just to reach the surface. So the sunlight warming your skin today actually began its journey during the last ice age. That's the kind of timescale we're dealing with when we talk about the Sun's unimaginable power. And this is just the beginning. Wait until we explore the even more extreme temperatures lurking deeper in the cosmos. But if you think the Sun's core is extreme, brace yourself for something even more mind-blowing. Meet WR102, the hottest known star in the universe, with a surface temperature that hits a jaw-dropping 210,000 degrees Celsius. That's over 14 times hotter than the Sun's core, and so intense that this star doesn't just shine, it practically screams its existence across the cosmos with a searing blue-white glow. WR102 belongs to a rare class called Wolf-Rayet stars, cosmic powerhouses that burn through their fuel at an insane rate. Unlike our Sun, which will quietly fade over billions of years, this star is in a hurry. It's literally tearing itself apart, blasting its own outer layers into space with stellar winds so powerful they could strip a planet bare in seconds. Imagine a candle not just melting, but violently hurling its own wax outward at millions of kilometers per hour. That's the kind of self-destructive fury we're talking about. What makes this even wilder? WR102 won't be around for long. Stars like this live fast and die young, exploding as supernova within a few 100,000 years. So while our Sun is the steady, reliable neighbor of the cosmos, WR102 is the cosmic equivalent of a fireworks finale, spectacular, blindingly hot, and gone in the blink of an astronomical eye. And this is just the second stop on our tour of the universe's most extreme temperatures. Trust me, things only get more intense from here. Now, let's take a step closer to home, but don't let that fool you into thinking things get any less extreme. Venus, our so-called sister planet, hides a shocking secret in its thick, toxic clouds. Here, lightning doesn't just crackle, it roars with temperatures reaching a staggering 30,000 degrees Celsius. That's 5 times hotter than the surface of the Sun itself. Venus's atmosphere is a pressure cooker of carbon dioxide, with clouds of sulfuric acid swirling in winds faster than hurricanes. All that chaos creates the perfect recipe for non-stop electrical storms. Unlike Earth's lightning, which lasts milliseconds, Venus's bolts are relentless, superheated by the planet's dense greenhouse gas-choked air. Picture a lightning strike so intense it could vaporize metal in an instant. That's the everyday weather on Venus. What's truly fascinating is what this tells us about planetary atmospheres. Venus shows us that extreme heat and pressure don't just create hellish conditions, they rewrite the rules of physics. Lightning this hot shouldn't exist on a rocky planet, yet Venus defies expectations. It's a reminder that even in our own cosmic backyard, nature has ways of cranking temperatures to unimaginable levels. And if you think that's wild, just wait. Our next stop takes us to temperatures so extreme, they rewrite the periodic table itself. Now, let's journey beyond our solar system to witness one of the universe's most violent and transformative events. When a massive star reaches the end of its life, it doesn't fade quietly, it goes out with a cataclysmic bang. A supernova explosion unleashes temperatures so extreme they hit a mind-bending 1 billion degrees Celsius, hotter than anything we've covered so far. At these unimaginable temperatures, physics as we know it gets turned upside down. The shockwaves racing outward from the collapsing star are so powerful they can fuse atoms together in an instant, creating heavy elements like gold, platinum, and uranium. Think about that: the gold in your jewelry or the uranium fueling nuclear reactors was forged in the heart of a dying star's final, fiery moments. What's even more astonishing is how brief this inferno lasts. While the temperatures spike to 1 billion degrees, the entire process can unfold in mere seconds. Yet in that blink of cosmic time, these explosions scatter newly minted elements across galaxies, seeding future stars and planets with the building blocks of everything from rocks to life itself. Supernovas remind us that destruction and creation are two sides of the same coin in the universe. And if you think 1 billion degrees sounds extreme, just wait. Our next stop takes us to temperatures 10 times hotter, where the universe's most energetic objects turn the heat dial all the way up. But if you thought supernovas were the ultimate cosmic furnaces, prepare to have your mind stretched even further. Deep in the hearts of distant galaxies, quasars take extreme temperatures to an entirely new level. These brilliant beacons are powered by supermassive black holes feasting on surrounding matter, and their coronas' halos of superheated gas reach a staggering 10 billion degrees Celsius. That's 10 times hotter than the core of a supernova, and hot enough to warp the very fabric of space-time around them. What makes quasars truly extraordinary isn't just their blistering heat, but the sheer energy they radiate across the universe. Their coronas glow with high-energy X-rays so intense they outshine entire galaxies, visible from billions of light-years away. Imagine a single object so luminous it could light up the cosmos like a lighthouse beam piercing through fog. Scientists believe these coronas form as magnetic fields near the black hole twist and snap, accelerating particles to near-light speeds and heating them to temperatures rivaling the first moments after the Big Bang. It's a cosmic pressure cooker where matter doesn't just burn. It's torn apart and reassembled in ways we're still struggling to understand. And here's the wildest part: quasars aren't rare relics of the past. They're still active today, reminding us that the universe holds pockets of unimaginable violence and energy hidden in plain sight. But if you're craving a break from all this heat, our next destination offers the perfect contrast. A place so cold it defies the very laws of physics. Now let's take a sharp turn from the universe's blazing infernos to its iciest depths. The Boomerang Nebula holds the record as the coldest natural place ever discovered, with temperatures plunging to a bone-chilling -272 degrees Celsius. That's just 1 degree above absolute zero, the theoretical limit where all molecular motion stops. This cosmic freezer isn't some lifeless void, it's the dramatic final act of a dying star. As the star sheds its outer layers at breakneck speeds, the gas expands so rapidly that it cools faster than anywhere else in nature. The result, a haunting, ghostly glow visible through telescopes, where dust and gas form eerie, symmetrical shapes that earned it the name Boomerang. What's truly mind-bending is how this nebula defies expectations. Most dying stars heat up their surroundings, but the Boomerang does the opposite, creating a pocket of cold so extreme it even chills the faint warmth of the cosmic microwave background, the afterglow of the Big Bang itself. Scientists believe this extreme cooling happens because the nebula's central star is losing mass at a rate thousands of times faster than our Sun. That furious outflow acts like a cosmic air conditioner, dragging temperatures down to nearly unimaginable lows. It's a reminder that even in the vastness of space, nature finds ways to break its own rules and leave us staring in wonder. And if you think that's cold, just wait until we explore the quantum weirdness that happens when we try to reach absolute zero itself. Now let's push the boundaries of cold even further, because as frigid as the Boomerang Nebula is, there's a temperature even more extreme in theory, though impossible to reach in reality. Absolute zero, the ultimate cold at -273.15 degrees Celsius, is the universe's unbreakable chill limit. No matter how advanced our technology gets, we can't quite touch this temperature, and quantum mechanics holds the key to why. At absolute zero, particles would stop moving entirely, but here's the catch: the laws of physics won't allow it. Thanks to a fundamental principle called the Heisenberg uncertainty principle, particles always retain a tiny bit of energy, even in the coldest possible conditions. It's like nature's way of saying close but not quite, but the real magic happens when we get close to absolute zero. At these extreme lows, matter starts behaving in ways that defy common sense. Take superfluidity, for example, where liquids like helium can flow without friction, climbing up the sides of containers as if gravity doesn't exist. Then there are Bose-Einstein condensates, a state of matter where atoms merge into a single quantum entity, acting more like waves than particles. These phenomena aren't just laboratory curiosities, they help us test the limits of quantum theory and even model conditions in neutron stars or the early universe. Scientists have come astonishingly close to absolute zero in labs, chilling atoms to within billionths of a degree. Yet that final step remains forever out of reach, a reminder that some cosmic rules are written in stone. So while we may never hit perfect zero, the journey to get there has unlocked some of the most mind-bending physics in existence, and that's a cool discovery in itself. Next up, we'll see how even the remnants of dead stars refuse to go quietly into the cold, as neutron stars glow with temperatures that would vaporize Earth in an instant. Now, let's turn our attention from the coldest extremes to one of the hottest remnants in the cosmos, neutron stars. These incredibly dense stellar corpses pack the mass of an entire star into a sphere no bigger than a city, and their surfaces blaze at a staggering 600,000 degrees Celsius. That's over 100 times hotter than the Sun's surface, and yet, believe it or not, neutron stars are actually cooling down. When a massive star explodes in a supernova, its core collapses under gravity's crushing force, squeezing protons and electrons together so tightly they merge into neutrons. The result is a neutron star, a cosmic powerhouse that retains unimaginable heat from its violent birth. Even though these objects are slowly losing energy, they still glow fiercely in X-rays, visible to telescopes as pinpoint beacons of extreme physics. But the real jaw-dropper, a single teaspoon of neutron star material would weigh billions of tons on Earth, and its sheer density would release enough heat to vaporize our planet's oceans in an instant. That's the kind of mind-bending energy we're dealing with here. These stellar remnants aren't just hot, they're laboratories for the universe's most extreme conditions, where matter is compressed beyond anything we can recreate on Earth. Neutron stars also spin at dizzying speeds, some rotating hundreds of times per second. and their magnetic fields are so strong they could strip the data from every credit card on Earth from thousands of light years away. Yet despite their ferocious energy, they're slowly fading, destined to cool into dark, cold husks over trillions of years, a reminder that even the universe's most extreme temperatures don't last forever. Up next, we'll bring things a little closer to home, comparing Earth's volcanic fury with the mind-blowing heat we've encountered in space. Now, let's bring the temperature scale back to something a little more familiar: Earth's own volcanic fury. Picture Hawaii's Kilauea volcano, where rivers of molten rock glow at a scorching 1,200 degrees Celsius. That's hot enough to melt steel, yet when we stack it against the cosmic extremes we've been exploring, it's almost like comparing a campfire to a supernova. Hawaii's lava flows are a spectacle of raw planetary power, with temperatures that can vaporize anything in their path. But here's the wild part: this inferno is downright chilly compared to the likes of neutron stars or supernova shockwaves. In fact, the Sun's surface, which we often think of as unbearably hot, is nearly 5 times hotter than Kilauea's lava. And remember WR102, that Wolf-Rayet star we talked about earlier? Its surface is a staggering 175 times hotter than Earth's most blistering volcanic flows. What makes Earth's volcanoes fascinating isn't just their heat, it's how they shape our planet. Lava builds new land, reshapes continents, and even influences climates. But in the grand theater of the universe, these eruptions are just a mild warm-up act. It's a humbling reminder that even our planet's most extreme temperatures are just a whisper in the cosmos's roaring symphony of heat. Next up, we'll visit a world where temperatures swing from blistering highs to icy lows in a single day. Mercury, the solar system's ultimate temperature roller coaster. Now, let's take a journey to Mercury, where the sun doesn't just rise and set. It brings a temperature swing so extreme it feels like 2 different worlds in a single day. By day, the surface bakes at a blistering 430 degrees Celsius, hot enough to melt lead. But when night falls, temperatures plummet to a bone-chilling minus 180 degrees Celsius, colder than Antarctica's deepest winter. What causes this wild roller coaster? Mercury's lack of a substantial atmosphere. Unlike Earth, where our atmosphere acts like a cozy blanket, trapping heat and moderating temperatures, Mercury has almost no air to hold onto warmth. Sunlight hits the surface with full force during the day, but as soon as the sun dips below the horizon, all that heat escapes into space, leaving the ground to freeze in the darkness. This extreme environment poses a massive challenge for spacecraft. NASA's messenger probe, which orbited Mercury, had to be built like a cosmic thermos layered with heat-resistant materials to survive the scorching days and insulated enough to endure the frigid nights. Even the sun-facing side of the spacecraft had to be protected by a sunshade, while the other side risked freezing solid. Mercury's temperature extremes aren't just a curiosity, they're a lesson in how atmospheres shape worlds. Without one, a planet becomes a land of brutal contrasts where survival demands more than just endurance. It demands engineering genius. Next, we'll explore another world where heat takes center stage, but in a very different way. Now, let's turn our attention to a world where fire reigns supreme: Jupiter's moon Io. While most moons are icy or barren, Io defies expectations with rivers of molten rock and lakes of lava that reach a staggering 1,600 degrees Celsius. That's hotter than any volcano on Earth, and here, eruptions aren't rare events, they're a constant spectacle. The secret behind Io's fiery chaos: Jupiter's immense gravity. As Io orbits the gas giant, the gravitational pull isn't just strong, it's relentless. The moon gets stretched and squeezed like cosmic taffy, generating immense friction deep inside. This process, called tidal heating, keeps Io's interior molten, fueling hundreds of active volcanoes that spew lava dozens of kilometers high. Some of these eruptions are so powerful, they've been spotted by telescopes from Earth, painting the moon in vivid yellows and oranges against the blackness of space. Unlike Earth's volcanoes, which go quiet between eruptions, Io's lava lakes never cool. The largest, Loki Patera, is wider than Lake Ontario and so hot it glows even in infrared images. Imagine a cauldron of liquid rock constantly churning with lava fountains that could dwarf Mount Everest. It's a landscape where the ground itself is unstable, reshaped daily by fresh flows and collapsing crust. Io's extreme volcanism isn't just a marvel, it's a window into the violent forces that shape worlds. While Earth's tectonic activity is driven by internal heat, Io shows what happens when a moon gets cooked from the outside in. Next, we'll step even further into the cold, to a relic from the dawn of the universe that holds a temperature record of its own. But now, let's journey from the searing heat of Io to the deepest cold the universe has to offer. The cosmic microwave background, a faint glow that fills every corner of space, holds the record for the coldest natural temperature we've ever measured, just 270 degrees Celsius below zero. That's only about 3 degrees above absolute zero, the theoretical limit where all motion stops. This icy whisper of light isn't just cold, it's ancient. It's the afterglow of the Big Bang itself, stretched and cooled over 13.8 billion years as the universe expanded. Imagine turning on a flashlight in a dark room, then watching its beam fade to a dim, even glow as the room grows to the size of a galaxy. That's essentially what happened to the universe's first light, now diluted into microwave radiation we can detect with sensitive telescopes. What makes this frigid glow so special? Its tiny imperfections. The cosmic microwave background isn't perfectly uniform. It has faint ripples, variations as small as 1 part in 100,000. These minuscule temperature differences are like cosmic fingerprints, revealing where matter was slightly denser in the early universe. Over billions of years, those dense spots became the seeds for galaxies, stars, and everything we see today. Scientists have mapped these variations in stunning detail, creating a baby picture of the cosmos just 380,000 years after the Big Bang. It's a snapshot of the universe before stars existed, when everything was a hot, dense soup of particles. Today, that same light serves as a universal thermometer, proving that even the emptiest voids of space aren't truly empty. They're filled with this primordial chill, the universe's oldest and most widespread cold. Next, we'll meet the cosmic misfits that blur the line between stars and planets, objects so strange they rain liquid metal from their skies. Now, let's turn our attention to one of the universe's most peculiar cosmic hybrids, brown dwarfs. These mysterious objects are the misfits of the cosmos, too massive to be planets but not quite massive enough to ignite as full-fledged stars. Imagine a celestial object that never quite made the cut for stardom, lingering in a strange twilight zone between worlds and suns. Brown dwarfs are fascinating because they defy simple classification. Some of them host atmospheres so bizarre they rain liquid iron, yes, actual droplets of molten metal, at temperatures around 1,000 degrees Celsius. Picture a storm where the raindrops aren't water but glowing, liquefied iron, sizzling as they fall through dense, turbulent skies. What makes these failed stars so unique? Unlike true stars, which shine brightly from nuclear fusion in their cores, brown dwarfs only flicker with the faint heat left over from their formation. They're cosmic embers cooling over billions of years, never quite reaching the temperatures needed to sustain the fusion reactions that power stars like our Sun. Yet, despite their dim glow, brown dwarfs can be surprisingly extreme. Some have atmospheres hot enough to vaporize rock, while others are so cool that water clouds might form, blurring the line between star and gas giant. Astronomers study them to understand how planets and stars evolve, revealing just how diverse the universe's temperature extremes can be. Up next, we'll explore how some stars don't just drift through space, they get violently ejected, leaving trails of superheated gas in their wake. Now let's shift our gaze to the cosmic speedsters of the universe, hypervelocity stars. These aren't your average stars lazily drifting through space. Imagine a star catapulted out of its galaxy at a staggering 1,000 kilometers per second, racing through the void like a bullet fired into the darkness. What makes these stars so extreme? As they hurtle through interstellar space, they slam into clouds of gas, creating colossal shock waves in their wake. These bow shocks heat the surrounding gas to millions of degrees, so hot that they glow intensely in X-rays, visible to telescopes designed to capture high-energy light. Picture a star plowing through the cosmos, leaving behind a trail of superheated gas like a cosmic wake behind a speeding boat. But how do stars reach such insane speeds? Most hypervelocity stars are thought to be ejected by the monstrous gravitational pull of supermassive black holes at the centers of galaxies. When a binary star system strays too close, one star gets captured while the other is flung outward at breakneck velocity, doomed to wander intergalactic space alone. These rogue stars don't just vanish into the dark. Their extreme speeds and the heat they generate offer astronomers a unique way to study the thin gas between galaxies, a region usually too faint to observe. By tracking these stellar outcasts, we uncover hidden details about the invisible material that fills the vast expanses of the universe. Next up, we'll dive into the heart of a pulsar wind nebula, where particles spin at nearly the speed of light, creating some of the most energetic phenomena in the cosmos. Now, let's zoom in on one of the universe's most powerful particle accelerators, pulsar wind nebulae. At the heart of these cosmic whirlpools lies a rapidly spinning neutron star, the dense corpse of a supernova explosion. This stellar remnant spins dozens of times per second, whipping its magnetic field around like an invisible lasso. That spinning motion does something extraordinary. It accelerates nearby particles to nearly the speed of light. Electrons and protons get caught in this magnetic maelstrom, reaching energies so intense they heat up to a blistering 10 million degrees Celsius. To put that in perspective, that's hotter than the core of our sun. The result, a glowing, high-energy cloud known as a pulsar wind nebula. The most famous example is the Crab Nebula, where this process creates an eerie blue glow visible across thousands of light years. The particles emit X-rays and gamma rays as they spiral along magnetic field lines, lighting up the nebula like a celestial neon sign. But here's the wild part: these particles don't just sit still. They race outward, expanding the nebula over centuries. Some even escape into interstellar space, carrying their extreme heat with them. It's a reminder that even in death, massive stars continue to shape the cosmos, turning their remains into engines of unimaginable energy. Next, we'll explore how Venus, despite being farther from the Sun than Mercury, became a pressure cooker with surface temperatures hot enough to melt lead. Now, let's turn our attention to a planetary cautionary tale: Venus, the solar system's ultimate pressure cooker. At first glance, you'd think Mercury, the closest planet to the Sun, would hold the title for hottest surface temperatures. But Venus, despite being farther away, is a staggering 460 degrees Celsius hot enough to melt lead. So what went wrong? The answer lies in a runaway greenhouse effect. Venus's thick atmosphere is 96% carbon dioxide, a greenhouse gas that traps heat like an invisible blanket. Billions of years ago, Venus may have had oceans, but as the Sun grew brighter, those waters evaporated. Water vapor, another potent greenhouse gas, thickened the atmosphere, trapping even more heat. This created a vicious cycle. Rising temperatures baked carbonates out of rocks, releasing more CO2 into the air. With no water left to absorb it through processes like Earth's carbon cycle, the gas kept accumulating. Today, Venus's surface pressure is 90 times Earth's, equivalent to being nearly a kilometer underwater, while its clouds rain sulfuric acid. Here's the chilling takeaway: Venus shows us what happens when a greenhouse effect spirals out of control. It's a stark reminder of how delicate planetary climates can be, and why understanding extreme temperatures isn't just about cosmic curiosity, but also about preserving our own world's balance. Next up, we'll visit a planet so scorching its own atmosphere is evaporating into space, the hellish world of Kelt 9b. Now, let's journey to a world so extreme it defies imagination. Kelt 9b, the hottest exoplanet ever discovered. Picture a planet where the daytime temperature hits a mind-blowing 4,300 degrees Celsius, hotter than some stars. This isn't just a scorching hot Jupiter, it's a place where the very laws of chemistry break down. On its star-facing side, molecules can't even hold themselves together. The intense radiation tears them apart, leaving only individual atoms swirling in the inferno. But the chaos doesn't stop there. Kelt 9b orbits so close to its host star that 1 year lasts just 36 hours, and the gravitational forces have stretched the planet into a football shape. The heat is so extreme that metals like iron and titanium don't just melt, they vaporize, creating a glowing tail of evaporated material that trails behind the planet like a comet. Scientists call this a planetary wind, a stream of gas being blasted into space by the star's relentless energy. What makes Kelt 9b even more fascinating is its inevitable fate. The planet is literally cooking itself alive, losing mass at an astonishing rate. Over millions of years, this cosmic furnace might evaporate entirely, leaving behind nothing but a ghostly core. This isn't just a record-breaking oddity. It's a glimpse into how planetary systems can push the limits of physics. Next, we'll explore how our own sun creates sudden, explosive temperatures that dwarf even this alien inferno. Shifting our gaze from distant exoplanets to our own cosmic backyard, let's talk about solar flares, the sun's explosive tantrums that unleash temperatures hotter than its core. When the sun's tangled magnetic fields suddenly snap and reconnect, they release mind-bending energy, heating plasma to a staggering 100 million degrees Celsius in mere seconds. That's hotter than the core of a hydrogen bomb. These eruptions aren't just spectacular light shows, they're cosmic powerhouses. The superheated plasma blasts outward as coronal mass ejections, sending shockwaves of charged particles racing through space. When these particles collide with Earth's magnetic field, they trigger dazzling auroras, painting the polar skies with shimmering greens and purples. But there's a flip side. The same storm can fry satellites, disrupt power grids, and even pose radiation risks to astronauts. What's wild is how routine this extreme physics is. The sun produces thousands of flares yearly, some small, others dwarfing our entire planet. Scientists classify the biggest as X-class flares, each one packing the energy of billions of atomic bombs. The Carrington event of 1859, for instance, was so powerful it set telegraph wires ablaze. Today, a similar flare could plunge continents into darkness. Yet these explosions also reveal the sun's inner workings. By studying them, we've learned how magnetic energy transforms into heat, a process that shapes stars across the universe. Next, we'll venture into the cosmos to meet a celestial oddity where temperatures plunge to depths colder than the void between galaxies. Now let's journey from the sun's blistering outbursts to the quiet chill of cosmic misfits, brown dwarfs. These strange objects are neither fully stars nor planets, but something in between. And one of them, known as WISE 0855, holds a record that might surprise you. It's the coldest brown dwarf ever discovered, with surface temperatures dipping to a frosty -13 degrees Celsius. That's colder than a winter night in Siberia, and shockingly mild compared to the usual scorching heat of stars. What makes this brown dwarf so fascinating is how it defies expectations. Unlike stars, it never ignited sustained nuclear fusion, so it just cools slowly over time, fading into cosmic obscurity. Yet it's not quite a planet either. It drifts alone in space, untethered to any star. Infrared telescopes revealed something even more intriguing. Its atmosphere might contain water clouds. Imagine that a failed star with weather patterns not unlike Earth's, except these clouds could be made of water vapor or even tiny ice crystals. This discovery blurs the line between stars and planets in ways astronomers never imagined. WISE 0855 is so cold that if you could stand on its surface ignoring the crushing gravity and lack of breathable air, you'd need just a heavy jacket rather than a heat shield. It's a reminder that the universe loves extremes, from 100 million degree solar flares to sub-zero celestial loners where the sky might drizzle ice. Up next, we'll explore how entire galaxies cluster together in a sea of superheated plasma, where temperatures reach staggering highs even in the emptiest-looking voids of space. But now, let's zoom out to an even grander scale where galaxies themselves gather in clusters, bound together by gravity. What looks like vast, empty space between them is anything but. In reality, these cosmic neighborhoods are filled with a superheated plasma, reaching temperatures of 100 million degrees Celsius. That's hotter than the core of most stars. This intergalactic gas is so energetic it emits X-rays, which observatories like Chandra can detect. Picture it as an invisible ocean of scorching particles, stretching for millions of light years. The heat comes from a mix of sources: galaxies colliding, supermassive black holes spewing energy, and shockwaves rippling through the cluster like cosmic tsunamis. What's truly mind-blowing is how this plasma shapes the universe. It acts as a cosmic pressure cooker, preventing galaxies from forming too many new stars by literally boiling away their gas. Yet without this searing hot medium, galaxy clusters wouldn't hold together the way they do. It's a delicate balance, a dance of extreme heat and gravity that keeps the universe's largest structures intact. Next, we'll rewind to a moment in Earth's history when an asteroid turned the sky into a fireball rivaling the sun's surface, proof that even our planet has flirted with cosmic extremes. Now, let's turn our attention to a moment when Earth itself experienced a taste of the sun's fury. On a quiet June morning in 1908, a blast ripped through the skies over Siberia with the force of 1,000 Hiroshima bombs. The Tunguska Event, as it's now known, was an asteroid explosion so powerful it flattened 80 million trees across 800 square miles, yet left no crater. The fireball generated temperatures of 30,000 degrees Celsius, matching the sun's surface. Eyewitnesses described a column of blue light splitting the sky, followed by a shockwave that knocked people off their feet hundreds of miles away. The heat was so intense it vaporized the asteroid before it could hit the ground, leaving only charred trees and shattered windows as evidence. Scientists believe the culprit was a stony asteroid around 60 meters wide that disintegrated 5 miles above Earth. The explosion released energy equivalent to 10 to 15 megatons of TNT, proof that even small space rocks can unleash cosmic-scale heat. What's chilling is that if this had happened over a major city, the devastation would have been unimaginable. This event serves as a fiery reminder that Earth isn't isolated from the universe's extremes. Next, we'll visit a world where winter temperatures plunge lower than anything our planet has ever recorded. Shifting our gaze from Earth's fiery past to the icy present of our planetary neighbor, let's explore the brutal winters of Mars. While the red planet might seem like a future home for humanity, its polar winters plunge to a bone-chilling -125 degrees Celsius, colder than any temperature ever recorded on Earth. Mars' thin atmosphere, just 1% as dense as Earth's, acts like a broken blanket, utterly failing to trap heat. Sunlight barely warms the surface during the day, and whatever little warmth gathers vanishes into space almost instantly at night. This extreme cold isn't just a number. It's a daily reality that would freeze unprotected humans solid in minutes. The poles are especially harsh, where carbon dioxide freezes out of the atmosphere, creating vast caps of dry ice. These seasonal frosts expand in winter, covering regions larger than some countries. Future colonists will need advanced heating systems and insulated habitats just to survive, let alone explore. What's fascinating is how Mars' cold reveals its fragile climate history. Scientists study these temperatures to understand how the planet lost its ancient lakes and rivers, transforming from a potentially habitable world into a frozen desert. Next, we'll witness the slow fade of stellar embers as white dwarfs cool across cosmic time. Now, let's turn our attention from the frozen deserts of Mars to the slow cosmic fade of dying stars. White dwarfs are the glowing embers of stars like our Sun's stellar corpses that no longer burn with nuclear fire but still radiate intense heat. When a star exhausts its fuel, it sheds its outer layers, leaving behind a dense, Earth-sized core scorching at around 100,000 degrees Celsius. But unlike the violent explosions of supernova, white dwarfs cool in near silence over unimaginable stretches of time. They start as searing orbs hotter than the sun's surface, but gradually lose their heat, dimming like a forgotten campfire. This cooling process is so slow that even the oldest white dwarfs in the universe, some nearly as old as the cosmos itself, are still far from reaching their final state. Here's the mind-blowing part. No white dwarf has ever cooled completely into a black dwarf, a cold, dark remnant. The universe simply hasn't existed long enough. It would take trillions of years, far longer than the current age of the universe, for one to fade entirely. Until then, these ancient stellar ghosts continue to glow faintly, their temperatures dropping degree by degree over eons. Studying white dwarfs is like reading the universe's history book. Their cooling rates help astronomers measure the ages of star clusters and even our galaxy. Next, we'll push the limits of heat itself as we explore the theoretical ceiling of temperature, the Planck scale. But before we dive into the coldest corners of space, let's push the boundaries of heat to their absolute limit. Imagine a temperature so extreme that the very laws of physics as we know them start to unravel. This is the Planck temperature, the hottest possible temperature in the universe, reaching an unimaginable 140 million trillion degrees Celsius. At this staggering heat, energy becomes so concentrated that particles collide with such force that gravity itself becomes as powerful as the other fundamental forces. Space and time lose their meaning, and the universe would resemble the chaotic conditions of the Big Bang. In fact, the Planck temperature is thought to have existed for just a fraction of a second after the birth of the cosmos, when all matter and energy were compressed into a single searing point. What makes this temperature truly mind-bending is that it represents the edge of our understanding. Beyond it, Einstein's theory of relativity and quantum mechanics, the twin pillars of modern physics, collapse. Here, scientists believe a theory of quantum gravity would take over, though we're still searching for the equations to describe it. For perspective, even the core of a supernova or the fury of a quasar is ice-cold compared to the Planck scale. It's a reminder that the universe still holds mysteries too extreme for our current science to fully grasp. Next, we'll swing back to the cold side of the spectrum, where Europa's hidden ocean defies freezing despite its frigid surface. Now let's journey from the universe's most extreme heat to one of its most fascinating cold mysteries. Europa, Jupiter's icy moon, hides a secret beneath its frozen crust, a vast subsurface ocean that remains liquid despite temperatures plunging to -160 degrees Celsius. How is this possible? The answer lies in the relentless gravitational tug of war between Jupiter and its other large moons. As Europa orbits Jupiter, the gas giant's immense gravity stretches and squeezes the moon, generating internal friction known as tidal heating. This process acts like a cosmic furnace, pumping enough warmth into Europa's core to keep its underground ocean from freezing solid. Imagine an ice-covered world where the ice itself acts as a thick insulating blanket, trapping heat from below while the surface remains bitterly cold. What makes Europa especially thrilling for scientists is that this hidden ocean could hold more than twice the volume of Earth's oceans combined. And where there's liquid water, there's potential for life. The Moon's icy shell likely harbors cracks and geysers that vent water into space, offering tantalizing clues about what might lurk beneath. Future missions like NASA Europa Clipper aim to study these plumes up close, searching for organic molecules or even microbial signatures. Europa's paradox, a liquid ocean in one of the solar system's coldest environments, shows how heat and cold can coexist in unexpected ways. Next, we'll unravel the temperature layers of Saturn's bizarre hexagon storm, where swirling winds create a thermal puzzle. Now let's turn our attention from Europa's icy depths to a storm of staggering scale and symmetry, Saturn's mysterious hexagon. This colossal weather feature, wider than two Earths side by side, swirls relentlessly around the planet's north pole with geometric precision. But what truly baffles scientists isn't just its shape, it's the wild temperature swings hidden within its layers. Saturn's hexagon acts like a towering atmospheric cake, where each slice reveals a different thermal story. At higher altitudes, where sunlight barely reaches, temperatures plummet to around -180 degrees Celsius. Yet dive deeper into the storm's churning belly, and you'll encounter pockets of warmth soaring to -120 degrees, a 60-degree swing across different layers of the same storm. This thermal roller coaster happens because the hexagon's jet stream, a six-sided river of wind screaming at 320 kilometers per hour, acts like a giant mixer. It churns up warmer gases from Saturn's depths while dragging frigid upper layers downward, creating swirling thermal contrasts visible to infrared telescopes. The storm's clean edges even seem to trap these temperature variations, preventing them from bleeding into Saturn's surrounding atmosphere. What keeps this polygon perfect for decades while Earth's hurricanes fade in days? The answer might lie in Saturn's lack of a solid surface. Without mountains or continents to disrupt airflow, the hexagon's winds can maintain their precise geometry, etching a near-permanent thermal fingerprint on the planet's pole. As we peel back another layer of Saturn's atmospheric enigma, our next stop takes us even farther into the cold, to the frozen relics of our solar system's birth, drifting in the Oort clouds near absolute zero darkness. Leaving behind Saturn's swirling hexagon, we now journey to the solar system's frozen frontier, the Oort cloud. This vast, dark shell of icy objects stretches nearly a light year from the Sun, where temperatures hover just 5 degrees above absolute zero. Here, comets remain frozen time capsules, preserving primordial ices at a bone-chilling -268 degrees Celsius, virtually unchanged since the dawn of our solar system. Unlike planets or asteroids, these distant wanderers never felt the Sun's warmth. Their surfaces are so cold that even volatile compounds like nitrogen and carbon monoxide freeze solid, forming exotic ices unseen in the inner solar system. When one occasionally gets nudged toward the Sun, it transforms into the glowing comet we recognize, but for billions of years, it existed in deep freeze, a perfect snapshot of the raw materials that built our cosmic neighborhood. What's truly remarkable is how these objects defy time. Without heat or radiation to alter their chemistry, Oort cloud comets are like celestial refrigerators, keeping their 4.5 billion-year-old ingredients pristine. Future missions to study them could reveal secrets about Earth's water origin or even the building blocks of life, delivered by similar icy visitors long ago. As we contemplate these ancient, frosty relics, our next destination brings us back to human-made extremes where scientists have engineered temperatures even colder than the Oort cloud's natural chill. Now, shifting our focus from nature's icy extremes to human-made fire, let's witness one of the most spectacular temperature events engineered by space travel. When spacecraft plunge back to Earth, they don't just glide smoothly through the atmosphere, they create a man-made inferno hotter than lava. The friction of re-entry heat surrounding air molecules to a staggering 3,000 degrees Celsius, transforming the vehicle's surface into a temporary artificial star visible for miles. This blazing plasma sheath isn't just for show, it's a deadly barrier that demands cutting-edge protection. Early space capsules like Mercury and Vostok used ablative heat shields that deliberately charred away layer by layer, carrying the heat with them. Modern spacecraft like SpaceX's Dragon employ advanced materials like Pika-X, a lightweight carbon composite that can withstand temperatures capable of vaporizing steel. What's fascinating is how this extreme heat actually helps slow the spacecraft. The superheated plasma creates a cushion of compressed air that acts like a natural brake, bleeding off thousands of miles per hour in speed. Astronauts experience this as the most intense phase of their return, watching flames lick past their windows while enduring deceleration forces up to 8 times Earth's gravity. From the space shuttle's glowing belly to China's Shenzhou capsules streaking across the night sky, these controlled fireballs represent humanity's mastery over one of spaceflight's most violent transitions. Next, we'll explore how even the Moon, often seen as a barren rock, harbors temperature extremes that defy expectations in its permanently shadowed craters. While spacecraft re-entry shows us how humans tame extreme heat, the Moon holds secrets in its darkest corners where cold reaches almost unimaginable depths. Hidden within permanently shadowed craters at the lunar poles, temperatures plummet to -250 degrees Celsius colder than the surface of Pluto. These icy traps never see sunlight, creating pockets so frigid they've preserved water ice for billions of years. What makes these shadows so extreme? Unlike Earth, the Moon has virtually no atmosphere to distribute heat, and its slight axial tilt means some crater floors near the poles are in eternal darkness. Sunlight skims their rims but never reaches inside, turning them into natural deep freezes. NASA, a lunar reconnaissance orbiter, measured these regions using infrared sensors, revealing temperatures low enough to freeze not just water but even gases like carbon dioxide and methane into solid form. The discovery of ice in these sunless vaults has transformed our understanding of the Moon. Scientists believe comets delivered this water over eons, and the ultra-cold shadows locked it away like a cosmic time capsule. Future lunar bases could mine these deposits for drinking water or split them into hydrogen and oxygen for rocket fuel, turning the Moon's harshest cold into an astronaut's greatest resource. Even more astonishing, some of these craters may contain cold traps where temperatures dip within 1 degree of absolute zero. That means the Moon harbors spots colder than any natural place we've found in the entire solar system. Next, we'll venture to Saturn's moon Titan, where methane takes the place of water in a bizarre, ultra-chilly version of Earth's weather cycle. Now let's journey to a world where the rules of weather are rewritten in deep freeze. Saturn's largest moon, Titan, is a place of surreal beauty where temperatures hover around -180 degrees Celsius, so cold that methane takes on the role water plays on Earth. Here, rivers of liquid hydrocarbons carve valleys into icy bedrock, vast methane lakes stretch across polar regions, and rainstorms drizzle gasoline like droplets in slow motion. Titan's thick nitrogen atmosphere, richer than Earth's, hosts a weather cycle straight out of science fiction. Sunlight triggers evaporation, sending methane gas into orange-hued clouds. When these clouds condense, they release methane rain that trickles for days due to Titan's low gravity. NASA Cassini spacecraft mapped lakes as large as North America's Great Lakes, some filled with enough liquid methane and ethane to fuel every car on Earth for decades. What makes Titan's cold so extraordinary isn't just the temperature, it's how familiar yet alien everything feels. Radar images show shorelines eroded by waves, dunes made of plastic like sand, and even seasonal changes where lakes shrink and expand. Beneath its icy crust, scientists suspect a subsurface ocean of water and ammonia, kept liquid by tidal heating from Saturn's gravity, a potential haven for exotic life. This moon's cryogenic water cycle challenges our ideas of habitability. While Earth storms are measured in hours, Titan's may last for years. Its lakes don't reflect sunlight like water. They're dark as tar, absorbing heat to slowly reshape the landscape. Next, we'll witness the Sun's fiery artistry, where plasma loops 20 times taller than Earth dance at temperatures hot enough to vaporize steel. Now, let's turn our gaze from the icy wonders of Titan to the Sun's dazzling displays of raw power. Solar prominences are colossal loops of superheated plasma, stretching tens of thousands of kilometers into space, some large enough to swallow Earth whole. At a scorching 50,000 degrees Celsius, these fiery arcs twist and dance along the Sun's magnetic fields, creating a spectacle that's both beautiful and terrifying. During a total solar eclipse, these prominences reveal themselves as crimson tendrils curling from the Sun's edge, glowing with the light of ionized hydrogen. What makes them so mesmerizing is their sheer scale and endurance. Unlike solar flares, which explode in minutes, prominences can linger for weeks, suspended like cosmic flames in the Sun's outer atmosphere. The physics behind these structures is just as fascinating. Charged particles spiral along magnetic field lines, trapped in a delicate balance between gravity and magnetic forces. Sometimes these loops become unstable, erupting into space as coronal mass ejection storms of plasma that can disrupt satellites and power grids on Earth. But for all their violence, solar prominences also hold clues to the Sun's inner workings. By studying their shapes and movements, scientists can map the Sun's hidden magnetic landscape, predicting space weather that affects our technology. Next, we'll step into the realm of human-made extremes, where scientists briefly recreate the universe's birth in a lab. Now, let's step away from the Sun's natural fury and into the realm of human ingenuity, where scientists have created temperatures that dwarf even the most extreme cosmic phenomena. In laboratories here on Earth, particle colliders like the Large Hadron Collider have achieved a staggering 5.5 trillion degrees Celsius, making them the hottest human-made environments in history. To put that into perspective, this temperature is over 300,000 times hotter than the core of the Sun. It lasts only for microseconds, but in that fleeting moment, something extraordinary happens. Ordinary matter breaks down into a primordial soup called quark-gluon plasma, the same state the entire universe existed in just fractions of a second after the Big Bang. This exotic plasma behaves unlike anything we encounter in daily life. Quarks and gluons, usually locked inside protons and neutrons, roam freely in a frictionless superfluid. Studying this state helps physicists unravel the universe's earliest moments, answering questions about how matter formed from pure energy. The conditions are so extreme that they warp our understanding of physics. Even the strongest magnetic fields and pressures in neutron stars pale in comparison to these lab-created infernos. Yet these experiments aren't just about breaking records, they're rewriting the story of cosmic origins, 1 microsecond at a time. Next, we'll explore another temperature mystery, this time on the icy outskirts of our solar system. Now, let's journey from Earth's scorching laboratories to the outer reaches of our solar system, where Neptune holds a puzzling thermal secret. Despite being farther from the Sun than Uranus, Neptune radiates significantly more internal heat, a mystery that has baffled scientists for decades. At first glance, both planets seem similar icy giants with frigid outer layers hovering around -220 degrees Celsius. But dig deeper and Neptune defies expectations. While Uranus barely emits any excess heat, Neptune glows with nearly 2.6 times more energy than it receives from the Sun. So what's cooking inside this distant blue world? One leading theory points to diamond rain. Deep within Neptune's atmosphere, extreme pressures may crush methane into diamonds that sink toward the core, releasing gravitational energy as they fall. This process could generate internal friction, heating the planet from within like a cosmic pressure cooker. Another clue lies in Neptune's turbulent weather. The planet boasts the solar system's fastest winds, screaming at over 2,000 kilometers per hour. This atmospheric chaos might help distribute heat more efficiently than Uranus's sluggish circulation. The contrast between these neighboring giants reminds us that distance from the Sun isn't the only factor governing planetary temperatures. Hidden dynamics from diamond showers to churning atmospheres can rewrite the rules of thermal physics. Next, we'll venture even deeper into cosmic heat extremes, where black holes turn infalling matter into glowing infernos. Now, let's turn our attention to one of the most extreme heat factories in the universe, the swirling chaos around a black hole. Picture this as cosmic debris spirals toward a black hole's event horizon. It doesn't just vanish quietly. Instead, it forms a superheated disk of matter called an accretion disk, where temperatures soar to millions of degrees. This isn't just any heat, it's the result of unimaginable friction. As gas, dust, and even entire stars get pulled inward, they collide and compress, converting their motion into blistering energy. The particles move so fast and smash together so violently that the disk glows fiercely across the electromagnetic spectrum, from visible light to X-rays. What's truly mind-blowing is the scale. Some supermassive black holes have accretion disks wider than our entire solar system, shining brighter than all the stars in their host galaxies combined. And yet, this spectacle is just the prelude. Once matter crosses the event horizon, it's gone from our observable universe forever. Scientists study these disks to understand how black holes grow and how they shape their galaxies. The heat they generate can even push surrounding gas away, effectively putting a brake on star formation. Next, we'll uncover another twist in our temperature tour, a mysterious cold layer hiding in Venus's scorching atmosphere. Just when you think Venus couldn't get any stranger, it throws another curveball our way. High above its scorching surface, where temperatures typically match a blazing oven, scientists stumbled upon something utterly unexpected, a sudden cold layer hiding in the clouds. Imagine a slice of space like chill, minus 175 degrees Celsius, sandwiched between layers of superheated atmosphere. This bizarre temperature drop happens about 125 kilometers above Venus's surface, in a region where the air is thin and sulfuric acid clouds swirl. What makes it so puzzling is that temperatures plunge sharply here, then climb back up as you go higher, defying conventional atmospheric models. It's like finding a patch of ice in the middle of a desert. Researchers suspect this cold zone might be linked to how Venus's thick atmosphere circulates. Unlike Earth, Venus has a super-rotating atmosphere. Its winds whip around the planet faster than the surface rotates, creating turbulent waves that could trigger these temperature swings. Some theories even suggest that rare chemical reactions in the clouds might be sucking heat out of the air, like a natural refrigerator in the sky. The discovery reminds us that even in a place as hellish as Venus, nature has a way of surprising us. Up next, we'll shift gears to another cosmic oddity, Jupiter's Great Red Spot, where stormy chaos generates its own heat signature against all odds. Now let's turn our attention to Jupiter, where a storm so massive it could swallow Earth whole has been raging for centuries. The Great Red Spot isn't just a marvel of size and endurance, it's also a cosmic heater, defying expectations by generating its own warmth. While the upper layers of this monstrous storm should be frigid, they're actually warmer than scientists ever predicted, creating a thermal mystery as deep as the storm itself. This swirling tempest, wider than our planet, reaches temperatures around 1,300 degrees Celsius in its upper atmosphere, far hotter than anything sunlight alone could explain. Normally, Jupiter's upper layers would be chilled by the void of space, but the Great Red Spot's violent winds seem to be converting energy into heat through sheer turbulence. Imagine a blender churning so fiercely it starts glowing. That's essentially what's happening here, but on a planetary scale. What's even more surprising is how this heat spreads. While the storm's core is relatively cooler, the warmth radiates outward, creating a thermal halo that puzzles researchers. Some theories suggest gravity waves, ripples in the atmosphere caused by the storm's motion, could be funneling energy upward, like ocean waves crashing and releasing spray into the air. Others propose that the spot's sheer depth, possibly plunging hundreds of kilometers below Jupiter's cloud tops, allows it to tap into the planet's internal heat reservoir. This self-heating storm reminds us that even in the outer solar system where sunlight is weak, nature finds ways to keep things fiery. Up next, we'll venture into the realm of human achievement, where scientists have created the coldest place in the universe, not in space, but right here on Earth. Now, let's shift from the cosmic heat of Jupiter to something far more chilling, literally. Scientists have achieved what nature hasn't by creating the coldest place in the known universe, right here on Earth. Using lasers and magnetic fields, they've cooled atoms to a mind-bending 0.0000000001 degrees Celsius above absolute zero. That's so close to perfect zero that atoms nearly stop moving entirely, entering a bizarre quantum state where the rules of physics as we know them start to break down. At these temperatures, atoms lose their individual identities and merge into a single wave of matter called a Bose-Einstein condensate. Picture a crowd of people moving in such perfect unison that they blur into one entity. That's what happens to atoms in this ultra-cold state. They behave less like particles and more like ripples on a pond, displaying quantum effects visible to the naked eye under lab conditions. This achievement isn't just about breaking records. It opens doors to understanding superconductivity, dark energy, and even the fabric of spacetime itself. By studying how matter behaves at these extremes, scientists hope to unlock secrets of the quantum world that could revolutionize technology, from ultra-precise sensors to quantum computers. So while the Boomerang Nebula holds the title for the coldest natural place, humanity has pushed the limits even further, proving that sometimes the most extreme frontiers aren't out in the cosmos, but in the quiet glow of a lab. Next, we'll return to the Sun to unravel why its outer atmosphere is mysteriously hotter than its surface. Now, let's circle back to our own star for a mystery that baffled scientists for decades. The Sun's outer atmosphere, called the corona, is actually millions of degrees hotter than its visible surface, a fact that defies common sense. After all, if you stand near a campfire, you expect the air to get cooler the farther you move away, not blisteringly hotter. So why does the Sun flip this logic on its head? The answer lies in the Sun's tangled magnetic fields. Imagine the Sun's surface as a bubbling pot of plasma, with magnetic field lines rising and twisting like invisible spaghetti. When these lines snap and reconnect, they release explosive energy in the form of nanoflares, tiny but frequent bursts that heat the corona to staggering temperatures. Think of it like cracking a whip. The energy starts at the handle but delivers its hottest punch at the very tip. Recent breakthroughs revealed another key player: magnetic waves. These vibrations ripple outward from the Sun's surface, transferring energy into the corona like ocean waves crashing onto a shore. NASA Parker Solar Probe finally confirmed this by flying closer to the Sun than any spacecraft before, detecting how these waves dump their energy into the corona's thin plasma. This isn't just academic curiosity. Understanding coronal heating helps us predict solar storms that can knock out satellites and power grids on Earth. Plus, it offers clues about other stars with similar mysteries. So next time you see an eclipse's shimmering corona, remember, you're looking at one of the solar system's most brilliant puzzles finally unraveling. Up next, we'll visit Pluto to explore how its frozen heart beats with surprising warmth. Shifting our gaze to the solar system's frozen frontier, Pluto reveals a chilling yet dynamic secret. This distant dwarf planet cradles a massive heart-shaped glacier of nitrogen ice, so cold it dips to -233 degrees Celsius, But here's the twist: this frozen heart isn't static. It pulses with slow, rhythmic movement, like a cosmic lava lamp operating on a timescale of centuries. The glacier, named Sputnik Planitia, behaves more like a fluid than a solid. Sunlight, faint as it is at Pluto's distance, provides just enough warmth to vaporize tiny amounts of nitrogen at the glacier's edges. This gas then drifts and refreezes elsewhere, creating a sluggish cycle of convection. Imagine pancake batter bubbling in a pan, but so slowly that a single bubble might take 500 years to rise. These movements carve bizarre polygonal patterns into the ice, visible to spacecraft like New Horizons. What's truly surprising is how these subtle temperature differences, just 10 to 15 degrees, drive this entire process. Warmer ice rises while colder material sinks, redistributing Pluto's surface features over millennia. This makes Sputnik Planitia the solar system's largest example of a slowly churning ice sheet, proving even the coldest places aren't entirely frozen in time. Up next, we'll encounter super-Earths where entire hemispheres glow with molten rock, a scorching contrast to Pluto's icy ballet. Now let's leap from the icy stillness of Pluto to the unimaginable infernos of distant super-Earths. Picture a world like Kepler 10b, where temperatures soar to 3,000 degrees Celsius, so extreme that entire hemispheres are nothing but vast, churning oceans of molten rock. This super-Earth, orbiting dangerously close to its star, is so hot that solid ground can't even exist. Instead, its surface is a seething mass of liquid lava, stretching as far as the eye could see. The heat is so intense that minerals don't just melt, they vaporize, creating an atmosphere thick with vaporized metals like iron and silicates. Imagine standing on such a planet if you could. The sky wouldn't be blue or even black, but a hazy, glowing mist of evaporated rock, shimmering under the relentless glare of its sun. What's even more fascinating is how these lava worlds defy our expectations of planetary behavior. On Earth, oceans circulate water, shaping climate and geography. But on Kepler 10b, the lava itself flows in slow, viscous currents, driven by the planet's scorching heat and gravitational tides. Some scientists believe these molten surfaces might even generate towering lava waves, crashing in slow motion under a sky of metallic vapor. And here's the kicker: Kepler 10b isn't alone. There are likely countless other super-Earths out there, each with its own version of this hellish landscape. These discoveries force us to rethink what planets can be, proving that the universe loves extremes, whether it's the frozen heart of Pluto or the firestorms of distant lava worlds. Next, we'll return to our own moon, where temperatures swing between blistering heat and bitter cold in a single day. Now, let's shift our focus from the scorching lava oceans of distant super-Earths to a place much closer to home, our very own moon. While it may seem tame compared to the extremes we've explored, the moon's temperature swings are nothing short of dramatic. During the long lunar day, surface temperatures can skyrocket to a blistering 120 degrees Celsius, hot enough to boil water instantly. But when night falls, they plummet to a bone-chilling -130 degrees, colder than Antarctica's deepest winter. For the Apollo astronauts, these extremes posed serious challenges. Their spacesuits had to withstand both the searing heat of direct sunlight and the frigid darkness of lunar night, all while keeping them alive in the airless void. Every step on the moon was a delicate dance between overheating and freezing, with no atmosphere to buffer the temperature swings. Even the lunar lander's metal surfaces would expand and contract violently, creaking under the strain of such rapid changes. But here's where modern technology comes in. Scientists and engineers are now eyeing the moon's polar regions as potential sites for future bases, where temperatures are far more stable. These areas, bathed in near-constant sunlight or perpetual shadow, offer pockets of relative moderation. Some craters at the poles, for instance, harbor permanently shadowed regions where temperatures hover around a manageable -50 degrees cold. but far easier to handle than the wild swings elsewhere. What's more, these polar zones may hold another key to survival: water ice. Hidden in those shadowed craters, this ice could provide drinking water, oxygen, and even rocket fuel for future missions. Imagine a lunar outpost nestled in one of these temperate zones, shielded from the moon's harshest extremes while tapping into its hidden resources. It's a far cry from the Apollo era's fleeting visits, and a testament to how far we've come in conquering the moon's unforgiving climate. Next, we'll venture into the realm of the unknown, where even temperature itself becomes a mystery: dark matter's hypothetical thermal behavior. Does it have a temperature at all, or does it exist in a state beyond our current understanding? Stay tuned as we explore one of cosmology's most puzzling questions. Now, let's step into the shadowy frontier of the cosmos, where even the rules of temperature seem to bend. Dark matter, the invisible glue holding galaxies together, might be the universe's ultimate thermal enigma. Unlike stars, planets, or even the frigid void of space, dark matter doesn't emit, absorb, or reflect light. So how could we ever measure its temperature? The answer might rewrite physics itself. Some theories suggest dark matter particles could collide, generating faint heat, but so far, no instrument has detected even a whisper of warmth. Other models propose it's utterly temperatureless, a cosmic ghost unaffected by the energetic dances of ordinary matter. Imagine a substance that doesn't care if it's near a supernova or drifting through the coldest nebula. Its behavior never changes. That's the puzzle scientists face. Here's where it gets stranger. If dark matter does have a temperature, it's likely bizarrely low, perhaps just a fraction above absolute zero. Yet even that's speculative. Some experiments hunt for hypothetical, warm, dark matter particles moving sluggishly, while others chase cold variants that barely budge. Each possibility would shape galaxies differently, leaving clues in the way they spin and cluster. What's certain, dark matter's thermal secrets, or lack thereof, could reveal why the universe looks the way it does. Is it a sea of ultra-cold particles sculpting galaxies with invisible hands, or something beyond temperature entirely, defying our understanding of heat and energy? For now, it remains one of cosmology's most tantalizing mysteries. Next, we'll uncover traces of a very different kind of heat, evidence that Mars, now a frozen desert, once cradled warm liquid water. Could those ancient hot springs have nurtured life? The clues are waiting. Turning our gaze from the mysteries of dark matter, let's land on the rusty surface of Mars, a world that once whispered with the warmth of flowing water. Today, it's a frozen desert where temperatures plunge to -125 degrees Celsius. But buried in its rocks are tantalizing clues that this barren landscape was once alive with hot springs, bubbling at a balmy 50 degrees Celsius. Scientists have pieced together this ancient puzzle using rovers like Curiosity and Perseverance. They've found mineral deposits that only form in the presence of liquid water, like silica and gypsum, clustered in patterns that scream hot springs. These aren't just puddles, they're signs of sustained hydrothermal activity, where groundwater heated by volcanic forces gushed to the surface. Imagine steam rising off Martian rocks, with temperatures cozy enough for Earth-like microbes to thrive. Here's where it gets thrilling. On Earth, hot springs are oases for extremophiles, tiny life forms that flourish in scorching or chemical-rich waters. If Mars had similar conditions billions of years ago, could life have sparked there too? The Perseverance rover is now drilling into Jezero Crater, an ancient lake bed fed by hot springs, hunting for fossilized microbes in the mudstone. Even if the water vanished long ago, its chemical fingerprints might still hold the answer. The irony is striking. Mars today is colder than Antarctica, yet it once hosted environments as warm as a tropical hot tub. This cosmic flip-flop hints at a dramatic past, perhaps a thicker atmosphere trapping heat, or volcanic networks acting like planetary radiators. Whatever the cause, those vanished hot springs are more than geological curiosities. They're a beacon in the search for life beyond Earth, proving that even the chilliest worlds can hide fiery secrets. Next, we'll measure the faintest warmth in the void, the sparse heat from all the stars combined, barely enough to keep a speck of space dust from freezing solid. It's the universe's background murmur, and it holds surprises. Now, let's step into the vast emptiness between the stars, where the cold is so profound it defies imagination. Even in the deepest reaches of interstellar space, there's a whisper of warmth just 3 degrees above absolute zero. This faint heat isn't from any single star, but the collective glow of every star in the universe, a cosmic background murmur that permeates the void. Picture this: if you were floating in the space between galaxies, far from any sun, you'd still feel this subtle warmth, barely enough to keep a single grain of ice from freezing solid. It's like standing in a pitch-black room with a single candle burning miles away. The light is almost imperceptible, but it's there, a reminder that even in the coldest places, the universe never quite lets go of heat entirely. This interstellar warmth comes from starlight that's traveled billions of years, stretched and diluted by the expansion of the cosmos. Every photon, every particle of light carries a trace of energy, and together they create this faint thermal blanket. It's not much, but it's enough to tell us that space is never truly empty, just incredibly quiet. What's fascinating is how this background heat compares to Earth's extremes. Our planet's coldest recorded temperature, -89.2 degrees Celsius in Antarctica, is practically tropical next to interstellar space. Yet even that bitter chill is nothing compared to the near absolute zero depths between the stars. It's a humbling reminder of just how mild and how special our little corner of the universe really is. Next, we'll witness a cataclysmic event where temperatures briefly outshine the entire galaxy, a collision so violent it hits 800 billion degrees in a flash. The universe's extremes never fail to astonish. Now, let's turn our attention to one of the most violent and dazzling events the universe has ever produced, a collision so extreme it rewrote the rules of physics. In 2017, astronomers witnessed something unprecedented. 2 neutron stars, the ultra-dense corpses of dead stars, spiraling toward each other and merging in a cataclysmic explosion. For a fraction of a second, the temperature at the heart of this collision soared to an unimaginable 800 billion degrees Celsius, hotter than the core of any star, hotter than even the aftermath of the Big Bang. This flash of heat was so intense it outshone every star in its galaxy combined, releasing a torrent of gamma rays visible across the cosmos. The collision forged heavy elements like gold, platinum, and uranium in mere seconds, elements that would eventually seed new solar systems. Imagine the entire jewelry section of Earth being forged in a single cosmic blast. What's even more remarkable is how fleeting this extreme heat was. Within moments, the fireball cooled, leaving behind either a heavier neutron star or a black hole, depending on the original masses. But in that brief instant, the universe gave us a front-row seat to one of its most extreme temperature events, a violent reminder of how dynamic and unpredictable space can be. This discovery didn't just rewrite textbooks, it confirmed long-held theories about where heavy elements come from and how neutron star collisions shape the cosmos. And to think, all that heat, all that brilliance was born from 2 dead stars spinning closer and closer until they couldn't resist the pull of gravity anymore. Up next, we'll revisit the hottest known planet, where molecules are torn apart daily by its star's fury. A world so extreme it defies imagination. Now, let's circle back to a planet so blisteringly hot it makes Mercury look like an icebox. Kelt 9b, the hottest known exoplanet, continues to baffle scientists with its extreme conditions. Recent observations reveal that this world isn't just hot, it's being vaporized alive by its own star. With daytime temperatures soaring to 4,300 degrees Celsius, Kelt 9b's atmosphere is so scorching that molecules like water and carbon dioxide can't even hold themselves together. They're ripped apart by the intense radiation, only to reform on the planet's slightly cooler night side, creating a brutal cycle of destruction and rebirth. What's truly mind-blowing is how this planet's star, Kelt 9, bombards it with ultraviolet radiation so fierce that the planet's atmosphere is literally boiling away into space. Astronomers have detected a glowing tail of evaporated metals trailing behind Kelt 9b like a cosmic comet. Imagine a world where your atmosphere isn't just thin, it's actively being stripped off your planet and blown into the void. But here's the kicker: Kelt 9b is so close to its star that it's tidally locked, meaning one side is perpetually baked in daylight while the other languishes in eternal night. This creates a temperature difference of over 1,000 degrees Celsius from one hemisphere to the other. If you thought Earth's weather extremes were dramatic, try surviving a day-night swing that could vaporize steel on one side and freeze it solid on the other. New research suggests Kelt 9b might not be long for this universe. At its current rate of atmospheric loss, this planet could eventually be reduced to nothing more than a barren, superheated core. It's a stark reminder that even in the cosmos, the most extreme environments often come with an expiration date. Up next, we'll ponder an even colder mystery: how close nature and science have come to reaching absolute zero, the ultimate chill. Shifting our focus from cosmic infernos to the deepest chills, let's explore the ultimate cold, absolute zero. At -273.15 degrees Celsius, this theoretical limit represents the complete absence of heat, where even atoms stop moving. Nature comes shockingly close in places like the Boomerang Nebula, where dying stars blast gas into space so fast it cools to just 1 degree above absolute zero. This eerie, ghostly cloud holds the title of the coldest natural place known, with temperatures barely warmer than the void itself. Yet here's the twist: scientists on Earth have outchilled even the cosmos. In labs, they've used lasers to slow atoms to a crawl, reaching temperatures within a fraction of a billionth of a degree above absolute zero. At these extremes, matter behaves in mind-bending ways, forming bizarre states like Bose-Einstein condensates, where atoms act as a single quantum wave. It's a realm where physics textbooks get rewritten daily. So, does perfect zero exist? The answer lies in quantum mechanics. Even in the emptiest reaches of space or the most advanced labs, there's always a whisper of energy, a quantum flicker that keeps absolute zero just out of reach. It's a cosmic tease. The colder we get, the more the universe reminds us that true stillness is impossible. Next, we'll unravel the paradox of sunspots, those dark patches on the sun that are somehow both scorching hot and surprisingly cool at the same time. Now, let's turn our attention to one of the sun's most fascinating puzzles: sunspots. At first glance, these dark patches seem like cooler regions on the sun's fiery surface, but don't let appearances fool you. Sunspots are still blisteringly hot, reaching around 4,000 degrees Celsius. The reason they look darker is simple. They're just slightly cooler than the surrounding plasma, which burns at a staggering 5,500 degrees. This temperature difference creates a striking visual contrast, making sunspots stand out like shadowy islands in a sea of light. But how do these cool zones form? It all comes down to the sun's powerful magnetic fields. When these fields become twisted and concentrated, they suppress the flow of heat from the sun's interior to the surface, creating a temporary chill, relatively speaking, of course. Despite their lower temperature, sunspots are anything but quiet. They're often the birthplaces of solar flares and coronal mass ejections, some of the most violent eruptions in our solar system. So while they might seem like calm, dark spots, they're actually hotspots of solar activity, proving that even the sun's cool zones are anything but mild. Up next, we'll take a step back and look at the universe's average temperature, a number that reveals just how cold space really is on the grandest scale. Now, let's zoom out to the grandest temperature scale of all, the universe itself. Believe it or not, space isn't just cold, it's chillingly uniform on average, sitting at a frosty -270.45 degrees Celsius. That's just a fraction above absolute zero, and it's all thanks to the relentless expansion of the cosmos. This frigid baseline comes from the cosmic microwave background, the faint afterglow of the Big Bang. As the universe stretches, that ancient light gets stretched too, shifting to longer, colder wavelengths over billions of years. Think of it like a cup of coffee left in an endless freezer. It'll keep cooling until it matches its surroundings. But here's the eerie part. This isn't just a snapshot of today's cold. The universe is on a one-way trip toward what scientists call heat death, where expansion spreads energy so thin that temperatures inch closer to absolute zero everywhere. Stars will burn out, black holes will evaporate, and eventually, even the last flickers of heat will fade into darkness. Yet for now, that average hides wild extremes, from blazing stars to icy nebulae, proving that even in a cooling cosmos, pockets of fire and frost keep the universe thrillingly alive. Now let's bring it all back home to Earth. While we've explored temperatures that defy imagination across the cosmos, our own planet's extremes seem almost cozy by comparison. The highest temperature ever recorded on Earth was a scorching 56.7 degrees Celsius in Death Valley, California. That's hot enough to fry an egg on the sidewalk, but it's practically a cool breeze next to the sun's surface or a supernova's fury. On the flip side, the coldest temperature ever measured on Earth was a bone-chilling -89.2 degrees Celsius in Antarctica. That's colder than a winter night on Mars, yet it's still a balmy paradise compared to the Boomerang Nebulas near absolute zero chill or the cosmic microwave background's relentless cold. What makes Earth special isn't just these extremes, it's the Goldilocks zone we occupy, where temperatures allow liquid water, diverse ecosystems, and human civilization to thrive. Out there in the universe, temperatures swing from unimaginable heat to soul-crushing cold, but here we're tucked into a narrow, life-friendly range. It's a humbling reminder of how rare and precious our planet's mild climate really is. So the next time you complain about a heat wave or a snowstorm, just remember, compared to the universe's most extreme temperatures, Earth's weather is downright pleasant. As we wrap up this incredible journey through the universe's most extreme temperatures, let's take a moment to reflect on the sheer scale of what we've explored. From the Big Bang's unimaginable heat to the icy depths of interstellar space, temperature has shaped every corner of the cosmos. We've witnessed stars so hot they boil themselves away, nebulas colder than the void itself, and planets where metals vaporize in the blistering glare of their suns. Each of these extremes tells a story of creation, destruction, and the delicate balance that makes our universe so astonishing. But here's the real wonder. Amid all these cosmic extremes, Earth sits in a perfect sweet spot. Not too hot, not too cold, just right for life to flourish. It's a humbling thought when you consider how rare and fragile our planet's conditions truly are. So the next time you step outside, whether it's into sunlight or snowfall, take a second to appreciate the Goldilocks miracle we call home. Now, we'd love to hear from you. Which of these mind-blowing temperature extremes left you the most amazed? Was it the searing fury of a quasar's corona or the ghostly chill of the Boomerang Nebula? Drop your thoughts in the comments below, and don't forget to like and subscribe for more deep dives into the universe's greatest mysteries. Thanks for joining us on this scorching and freezing adventure through space.